are pushing ahead towards the end of our semester with kinetics. Got a couple more videos that we need to work through here. We're currently working on our integrated rate laws, and I want to go into half-life calculations. Half-life is the time it takes for half of the initial amount to react, or we're going to be talking about nuclear decay, radiological decay, and that's half of it, the original amount to decay. Now I want you to notice something critical here. When we're dealing with second order and zero order, both of these half-lives depend on the initial amount present. Wonderfully, because it provides us with some great ways to do things medically as well as radiological dating in archaeology and fields such as that. This does not depend upon the initial amount. So that means that if I have graphs, let me show you very quickly what the graph would look like for zero order. Just as a reminder, if we had molarity versus time and it was zero order, we'd have a straight line. So that's pretty obvious that it's zero order in that case. Now, if it's first or second, you notice we have a decreasing curve for both of them. And yes, one does curve down a little bit more sharply, but still that's not always easy to tell. Well, all you have to do to determine whether your process, and I've seen questions like this, by the way, whether it's first order or second order, is do a couple of half-lives. So start anywhere. I'm just going to start at the top like the picture did, but you can start anywhere and you'll have the same values. So if I start at 0.1 and I cut it in half, I get 0.05 right here. And I look at the time that it takes, and this is 100 seconds. Now I start at 0.05. Really, again, you can start anywhere and prove the same point. Go down to 0.025, and sure enough, it takes 100 seconds because half-life does not depend on initial amount. And then if we do this yet a third time, it's still 100 seconds. So that would be your evidence to support a claim that this data represents first-order kinetics. You can actually do this, and we will be doing this with your crystal violet data. Now let's take a look here. 0.2, down to 0.1 gave us a half-life of 50 seconds. And then we cut that in half to 0.05, and we have a half-life of 100 seconds. And then we cut that in half again, and we go from, let's see, 150 to 350. We have one of 200 seconds. So you notice that as you decrease your starting amount, you increase your half-life. So if half-life was increasing, that could support a claim that this was a second-order reaction. Now let's take a look at a couple of problems with this. I don't like to use any shortcut mathematics. I know you saw some when you were possibly in your math classes. I want us to use our original formulas that we derived. We have second-order decomposition, and it gives us our half-life. So I want to write down both formulas. That's the best way to start these. As soon as you understand, either because it's given or you look at the units for K, you want to write down your formulas. So my half-life formula for this one is that my half-life for zero order, if you look up at your chart, your half-life is 1 over K times your concentration of A naught, whatever your A is. In this case, it's N2O. And then we would have, I'm going to go ahead and put the N2O this time. N2O at time t is equal to KT plus 1 over N2O at time 0. All right, so it's pretty much what we saw before. We've already worked with this equation. Now we're just going to combine the equations. Let's see what's given. We are given the half-life, 75, and notice that it's in minutes. It's important. We're given the time, and it's also in minutes, so we're in good shape there. So that's 150 minutes. Now, our initial concentration of A naught is 2 times 10 to the minus 2, and we can put that in here since our A naught references the N2O. Now, what we're after, this is our ultimate unknown. But you notice right now, I actually have two unknowns in this equation. Well, that's okay, because our first equation gives us our value for K. So what you do is you solve this equation for K, and then we're going to substitute that value in right there. And then secondly, you're going to solve it for your original concentration. Now, if we do that, we find that K is equal to 0.667 and that N2O at time t is equal to 6.67 times 10 to the minus third. Okay, so that would be for a second order example. Now, this would be now using that information to continue. How long would it take for 40% to decompose? So this reiterates doing just a more straightforward formula using this. But I wanted to show you that we can't assume any values here like we did on the first order. We actually need real values here, and fortunately we have it. If 40% decomposed, that means 60% remained. Be very careful whether the question says is giving you the amount remaining or decomposing. And so I just need to take 60% of this value here, and that's going to be my N at time t. I already have my K from the previous problem, so again, it's simply plugging in. The only difficulty is making sure you capture the right math formula, the right equation for the right occasion, and then check your units before you forge ahead too quickly. All right, and we solve this, and you should get 50 minutes. All right, now I do want to do one more before our time's up here on this video. I want to do one to show you just radioactive decay. And since so many of you are going to be going into medical fields, I like to find ones that talk about the medical applications of radiological decay. So we have radioactive P32. We are given a half-life, so you might want to go ahead and jot that down. You can either list your givens, or another way to do this that I think is really helpful is to just point here and label it with the correct symbol. So you could put T1/2 there, and then you could put your T there. Color doesn't show up very well for us here. All right, now this is kind of unique. You notice in this reaction we've got some very different values for our concentrations. So if we go back to the way that we did first order, because it does tell us it's first order, if you go back to that way that I did earlier with this rearrangement, A at time t over A naught, the other reason I like this form of this, while it doesn't help us as much graphically, mathematically, if this is our unknown, I think it helps us see those comparisons there. Now, anything we would do to convert this would cancel anything we converted with that. So we can effectively use any way of marking the amount of that substance. So I'm going to go ahead and plug that in. I've got natural log of A at time t, which is 8,500, over A naught, which was 10,000. And it's just counts per minute. I'll pull out my Geiger counter, and I think you'll get an idea of what is meant by counts per minute, because you can honestly hear it click as it's counting the different particles, whether it be alpha or beta particles. Now, that's equal to minus KT. Now, this is our ultimate unknown. So we need to have a way to find K. Well, that's where our half-life comes into play, because T1/2 is equal to 0.693 over K. And since we know our T1/2 is 14, we can solve this for K. So first, we're going to solve this equation for K, and then we're going to substitute that K in here. And I'm not going to spend time on algebra on this video. I'm assuming you can do your algebra, and I'm assuming you're going to check me in my algebra. And I came up with 3.28 days. So, all right, now that's it for these integrated rate laws. We've spent a lot of time on concentration effects on rates, and we're going to really get a taste of temperature in a catalyst. There's not a whole bunch we want to talk about there. So until we are back to those videos, this is signing off.